Title: Java Generics Demystified, Writing Type-Safe and Reusable Code. Opening shot. The host stands in front of a whiteboard with generics in Java written on it, ready to explain the essential concepts of generics. Hello, Java enthusiasts! Today, we're diving deep into the world of Java generics. Generics are like the Swiss Army knife of Java programming, allowing you to write type-safe and reusable code. Let's unlock the power of generics in Java. Slide 1: Generics in Java. First, let's understand why generics are so important. Concept 1. What are generics? Generics provide a way to create classes, interfaces, and methods that operate on types yet to be specified. They enable you to write code that works with different data types while maintaining type safety. Visuals: diagram illustrating generics. In Java, generics are represented using angle brackets and are commonly used with collections and custom data structures. Visuals: code snippet illustrating the use of generics. Concept 2: Type safety. Generics offer type safety, ensuring that you can catch type-related errors at compile time rather than runtime. This means fewer surprises and more reliable code. Visuals: code snippet illustrating type safety with generics. Concept 3: Generic classes and interfaces. Let's explore how to create your own generic classes and interfaces. 1. Generic classes. You can create a generic class by adding type parameters within angle brackets after the class name. Visuals: code snippet illustrating a generic class. 2. Generic interfaces. Interfaces can also be generic, allowing you to define a contract that works with specific types. Visuals: code snippet illustrating a generic interface. Concept 4: Generic methods. Generics are not limited to classes and interfaces. You can also create generic methods that work with specific types on a per-method basis. Visuals: code snippet illustrating a generic method. Concept 5: Wildcards. Wildcards are a powerful feature of generics that allow you to work with unknown types. 1. Unbounded wildcards. Represents an unknown type. Visuals: code snippet illustrating an unbounded wildcard. 2. Upper bounded wildcards. Extends T, specifies that the type must be a subtype of T. Visuals: code snippet illustrating an upper bounded wildcard. 3. Lower bounded wildcards. Super T, specifies that the type must be a supertype of T. Visuals: code snippet illustrating a lower bounded wildcard. Concept 6: Best practices. To make the most of generics in Java, consider these best practices. 1. Use descriptive names. Choose meaningful names for your generic type parameters. 2. Favor generics over raw types. Use generics instead of raw types to ensure type safety. 3. Use wildcards for flexibility. When designing APIs, use wildcards to make them more flexible and usable. Visuals: list of generics best practices. Generics are a powerful tool in Java, allowing you to write more versatile and type-safe code. Closing shot. The host smiles. Thank you for joining us in this tutorial. If you found this information valuable, please like, subscribe, and hit that notification bell for more Java programming insights. Stay tuned for our next Java adventure. End with an engaging outro screen displaying the course name and a call to action to subscribe and stay updated. Fade out. Title: Understanding Object-Oriented Programming, OOP, Concepts in Java. Opening shot. The host stands in front of a whiteboard with OOP concepts in Java written on it, ready to explain the fundamental principles of object-oriented programming in Java. Hello everyone! Welcome to today's tutorial, where we'll delve into the world of object-oriented programming, OOP, concepts in Java. Whether you're a beginner or looking to reinforce your understanding, this video will break down the core principles of OOP. Slide 1: Object-Oriented Programming Concepts in Java. Java is a popular programming language known for its robust support of OOP. Let's explore the key concepts. Concept 1: Objects. At the heart of OOP lies the concept of objects. Objects are instances of classes and represent real-world entities, or concepts. They encapsulate data and behavior. Visuals: diagram of an object with data and behavior. Concept 2: Classes. Classes are blueprints for creating objects. They define the structure and behavior of objects of a specific type. Visuals: diagram showing a class with attributes and methods. Concept 3: Inheritance. Inheritance is a mechanism that allows a new class, subclass, or derived class to inherit properties and behaviors from an existing class, superclass, or base class. Visuals: diagram illustrating class inheritance. Concept 4: Polymorphism. Polymorphism allows objects of different classes to be treated as objects of a common superclass. It enables flexibility and extensibility in your code. Visuals, example of polymorphism with different subclasses. Concept 5. Encapsulation. Encapsulation is the practice of hiding the internal details of an object and providing a public interface to access and modify its state. It ensures data security and prevents unauthorized access. Visuals, diagram showing encapsulation with private and public access. Concept 6. Abstraction. Abstraction involves simplifying complex reality by modeling classes based on essential properties and behaviors. It focuses on what an object does, rather than how it does it. Visuals, diagram illustrating abstraction. Concept 7. Association and aggregation. Association represents a relationship between objects, while aggregation is a specialized form of association, denoting a whole-part relationship. Visuals, diagrams showing association and aggregation. Understanding these core OOP concepts is crucial for writing clean, modular, and maintainable Java code. Closing shot. The host smiles. Thank you for joining us in this tutorial. If you found this information helpful, please like, subscribe, and hit that notification bell for more programming insights. Stay tuned for our next Java tutorial. Title: Understanding Classes and Methods in Java, Building the Foundation. Opening shot. The host stands in front of a whiteboard with classes and methods in Java written on it, ready to explain the fundamental concepts of classes and methods in Java. Welcome, fellow coders, to another exciting Java tutorial. Today, we're going to dive deep into the core building blocks of Java programming, classes, and methods. Understanding these concepts is essential for creating powerful and organized Java applications. Slide 1. Classes and methods in Java. Let's break it down, starting with classes. Concept 1. Classes. In Java, a class is like a blueprint for objects. It defines the structure and behavior that objects created from that class will have. Think of it as a cookie cutter for making cookies. The class defines what the cookie should look like. Visuals, diagram of a class with attributes and methods. To create a class in Java, you'll use the class keyword, followed by the class name. Inside the class, you can declare attributes, variables, and methods, functions that define the object's properties and behavior. Visuals, code snippet illustrating a Java class. Concept 2. Methods. Now let's talk about methods. Methods are functions defined within a class that perform specific actions or computations. They are like the actions you can perform with a cookie once it's baked, such as eat or share. Visuals, diagram showing methods within a class. To define a method in Java, you'll need to specify its name, return type, what it gives back, and any parameters it accepts. Methods encapsulate a specific functionality that can be reused throughout your program. Visuals, code snippet illustrating a Java method. Concept 3. Object creation. Once you have a class defined, you can create objects from that class. Objects are instances of the class, just like each cookie you bake is an instance of the cookie cutter. Visuals, diagram showing object creation. To create an object in Java, you use the new keyword, followed by the class name and parentheses. This allocates memory and initializes the object. Visuals, code snippet illustrating object creation. Concept 4. Method invocation. Now how do you use those methods you defined in your class? You invoke or call them on objects. Think of it as eating a cookie. You perform an action on a specific cookie. Visuals, diagram showing method invocation. To call a method on an object in Java, you use the object's name, followed by a dot, and then the method name along with any required arguments. Visuals, code snippet illustrating method invocation. Understanding classes and methods forms the foundation of Java programming. It allows you to create organized, reusable, and efficient code. Closing shot. The host smiles. Thank you for joining us in this tutorial. If you found this information helpful, please like, subscribe, and hit that notification bell for more Java programming insights. Stay tuned for our next Java adventure. Title: Objects and Methods in Java. Unleashing the Power of Code. Opening shot. The host stands in front of a whiteboard with objects and methods in Java written on it, ready to explain the concepts of objects and methods in Java. Hello, fellow Java enthusiasts. Today, we're diving deep into the world of objects and methods in Java. These are the building blocks that allow you to create dynamic, functional, and organized programs. Let's unlock their potential. Slide 1. Objects and methods in Java. First, let's get acquainted with objects. Concept 1. Objects. An object is a fundamental concept in Java. Think of it as a real-world entity that has both state, attributes are properties, and behavior, actions, are methods. Objects are instances of classes. Visuals, diagram of an object with attributes and methods. In Java, you define objects by creating classes. A class is like a blueprint or template for objects. It specifies what attributes and methods an object created from that class will have. Visuals, code snippet illustrating a Java class. Concept 2, methods. Now let's explore methods. Methods are functions defined within a class. They represent the actions or behaviors that an object can perform. You can think of them as the verbs in your code. Visuals, diagram showing methods within a class. To create a method in Java, you'll need to specify its name, return type, what it gives back, if anything, and any parameters it accepts. Methods encapsulate specific functionality that can be reused throughout your program. Visuals, code snippet illustrating a Java method. Concept 3, object creation and method invocation. Creating objects and invoking methods on them is where the magic happens. 1. Object creation. To create an object from a class, you use the new keyword followed by the class name and parentheses. This allocates memory and initializes the object. Visuals, code snippet illustrating object creation. 2. Method invocation. Once you have an object, you can invoke or call its methods using the object's name, followed by a dot, and then the method name along with any required arguments. Visuals, code snippet illustrating method invocation. Concept 4, object interaction. Objects can also interact with each other. They can pass information or invoke methods on other objects, allowing for complex and dynamic program behavior. Visuals, diagram showing object interaction. Understanding how objects and methods work together is essential for writing efficient and organized Java code. Closing shot. The host smiles. Thank you for joining us in this tutorial. If you found this information valuable, please like, subscribe, and hit that notification bell for more Java programming insights. Stay tuned for our next Java adventure. Title: Java's Building Blocks, Inheritance, Polymorphism, and Interfaces Demystified. Opening shot. The host stands in front of a whiteboard with inheritance, polymorphism, and interfaces in Java written on it, ready to explain these key concepts. Hello, Java enthusiasts! Today, we're diving into the core concepts that make Java such a versatile and powerful language. Inheritance, polymorphism, and interfaces are like secret weapons in your coding arsenal. Let's demystify them. Slide 1, Inheritance, Polymorphism, and Interfaces in Java. First up, let's unravel the power of inheritance. Concept 1, Inheritance. Inheritance is like the passing down of characteristics from one generation to the next. In Java, it allows you to create a new class, the child or subclass, that inherits properties and behaviors from an existing class, the parent or superclass. Visuals, diagram illustrating class inheritance. Using the extends keyword in Java, you can establish this inheritance relationship. The child class gains access to the attributes and methods of the parent class, making your code more organized and efficient. Visuals, code snippet illustrating class inheritance. Concept 2, polymorphism. Polymorphism, derived from Greek meaning many shapes, is the ability of objects of different classes to be treated as objects of a common superclass. This concept brings flexibility and extensibility to your code. Visuals, diagram illustrating polymorphism. To achieve polymorphism in Java, you can use method overriding. When a subclass provides its own implementation of a method defined in the superclass, it can be invoked in place of the superclass method. Visuals, code snippet illustrating method overriding. Concept 3, interfaces. Interfaces define a contract for classes. They are like a blueprint specifying a set of methods that must be implemented by any class that implements the interface. Visuals, diagram illustrating an interface. Java allows a class to implement multiple interfaces, enabling it to inherit behaviors from multiple sources. Interfaces are a key part of achieving abstraction and code reusability. Visuals, code snippet illustrating interface implementation. Concept 4, polymorphism with interfaces. Combining polymorphism and interfaces can lead to powerful code structures. You can use interfaces to define a common set of methods that different classes implement in their own unique ways. Visuals, diagram illustrating polymorphism with interfaces. This allows you to treat objects of various classes that implement the same interface as interchangeable, providing a high degree of flexibility. Visuals, code snippet illustrating polymorphism with interfaces. Understanding inheritance, polymorphism, and interfaces is crucial for writing modular, reusable, and scalable Java code. Closing shot. The host smiles. Thank you for joining us in this tutorial. If you found this information valuable, please like, subscribe, and hit that notification bell for more Java programming insights. Stay tuned for our next Java adventure. Title: Mastering Java, Exception Handling, Ensuring Robust Code. Opening shot. The host stands in front of a whiteboard with exception handling in Java written on it, ready to explain the important concept of exception handling. Welcome, Java enthusiasts! Today, we're diving deep into the world of Java exception handling. Exception handling is like your code safety net, ensuring that it gracefully handles unexpected situations. Let's learn how to make our Java programs robust. Slide 1. Exception handling in Java? First, let's understand what exceptions are and why they matter. Concept 1. Exceptions. An exception is an unexpected or erroneous event that occurs during the execution of your program. It can be anything from dividing by zero to trying to access a non-existent file. Visuals, diagram illustrating exceptions. Java uses exceptions to deal with these unexpected situations. When an exception occurs, it disrupts the normal flow of your program and throws an object known as an exception object. Visuals, code snippet illustrating an exception. Concept 2. Exception handling. To handle exceptions gracefully, Java provides a mechanism called exception handling. It allows you to catch and respond to exceptions, rather than letting them crash your program. Visuals, diagram showing exception handling process. In Java, exception handling is done using try-catch blocks. You try a block of code that might throw an exception, and if one occurs, you catch it and specify how to handle it. Visuals, code snippet illustrating a try-catch block. Concept 3. Checked versus unchecked exceptions. There are two types of exceptions in Java: checked and unchecked. 1. Checked exceptions. These are exceptions that are checked at compile time. You must either handle them using try-catch or declare them in your method's throws clause. Visuals, code snippet illustrating a checked exception. 2. Unchecked exceptions. Also known as runtime exceptions. These exceptions occur at runtime and are not required to be caught or declared. They typically indicate programming errors. Visuals, code snippet illustrating an unchecked exception. Concept 4. Finally block and custom exceptions. In addition to try-catch blocks, Java also provides the finally block, which allows you to specify code that runs regardless of whether an exception is thrown or not. Visuals, code snippet illustrating a finally block. Furthermore, you can create your custom exceptions by extending the exception class. This is useful when you want to define your specific types of exceptions. Visuals, code snippet illustrating a custom exception. Concept 5. Best practices. To ensure robust and maintainable code, here are some exception handling best practices. 1. Catch specific exceptions. Catch the most specific exceptions first. 2. Use meaningful error messages. Provide clear error messages to aid debugging. 3. Avoid catch-all blocks. Avoid using generic catch blocks that catch all exceptions indiscriminately. Visuals, list of exception handling best practices. Exception handling is an essential skill for every Java developer. It helps your code gracefully handle unexpected situations and ensures your applications remain robust. Closing shot. The host smiles. Thank you for joining us in this tutorial. If you found this information valuable, please like, subscribe, and hit that notification bell for more Java programming insights. Stay tuned for our next Java adventure. Title: Java File Input and Output, Managing Data Like a Pro. Opening shot. The host stands in front of a whiteboard with file input and output in Java written on it, ready to explain the essential concepts of file handling in Java. Greetings, Java enthusiasts! Today, we're diving into the world of file input and output in Java. Whether you're reading data from a file or writing data to one, file handling is a fundamental skill for every developer. Let's learn how to manage data like a pro. Slide 1. File input and output in Java. First, let's understand why file handling is so important. Concept 1. File handling. File handling is the process of reading from and writing to files on your computer's storage. Files can store data, configurations, logs, and more. Java provides powerful mechanisms to work with files. Visuals, diagram illustrating file handling. In Java, you can perform file input and output operations using classes from the Java I/O package, such as file input stream, file output stream, buffered reader and buffered writer. Visuals, code snippet importing, file-related classes. Concept 2, reading from files. Reading data from a file is a common task. Let's see how it's done. 1. Using file input stream. You can use file input stream to read bytes from a file. Wrap it with a buffered reader for more efficient character-based reading. Visuals, code snippet illustrating file reading. 2. Using file reader if you're working with text files. File reader is a convenient choice. It reads characters directly and can also be wrapped with buffered reader. Visuals, code snippet illustrating text file reading. Concept 3, writing to files. On the flip side, writing data to a file is just as important. 1. Using file output stream. You can use file output stream to write bytes to a file. Wrap it with a buffered writer for character-based writing. Visuals, code snippet illustrating file writing. 2. Using file writer for text-based data. File writer is handy. It allows you to write characters directly and can also be wrapped with buffered writer. Visuals, code snippet illustrating text file writing. Concept 4, exception handling. Whenever you're dealing with file operations, it's crucial to handle exceptions properly. File-related methods can throw I/O exceptions, and it's good practice to catch and handle them. Visuals, code snippet illustrating exception handling in file operations. Concept 5, best practices. To ensure efficient and error-free file handling, consider these best practices. 1. Close files properly. Always close files after reading or writing to prevent resource leaks. 2. Use try with resources. In Java, you can use try with resources to automatically close resources like files. 3. Check file existence. Before reading or writing, check if the file exists to avoid unexpected errors. Visuals, list of file handling best practices. Understanding file input and output is an invaluable skill for any Java developer. It allows you to work with data stored in files, making your applications more versatile and data-driven. Closing shot. The host smiles. Thank you for joining us in this tutorial. If you found this information valuable, please like, subscribe, and hit that notification bell for more Java programming insights. Stay tuned for our next Java adventure. Title: Exploring Java's Hidden Gems, Enumerations, and Nested Classes. Opening shot. The host stands in front of a whiteboard with enumerations and nested classes in Java written on it, ready to explain these powerful concepts. Hello, fellow Java enthusiasts. Today, we're diving into the world of Java's hidden gems, enumerations, and nested classes. These features add depth and flexibility to your code, allowing you to create elegant and organized solutions. Let's uncover their magic. Slide 1, Enumerations and Nested Classes in Java. First, let's unravel the power of enumerations. Concept 1, Enumerations, enums. An enumeration, or enum, is a special data type in Java that represents a fixed set of constants. Enums make your code more readable and maintainable by providing a way to define and work with predefined values. Visuals, diagram illustrating an enumeration. To declare an enum in Java, you use the enum keyword followed by the enum name and the constant values inside curly braces. Visuals, code snippet illustrating an enum declaration. Concept 2, using enums. Now that you've declared an enum, you can use it to create variables and switch between predefined values. 1. Creating enum variables. You can declare variables of the enum type and assign them specific enum values. Visuals, code snippet illustrating enum variables. 2. Switch statements with enums. Enums are often used in switch statements to handle different cases elegantly. Visuals, code snippet illustrating a switch statement with enums. Concept 3, nested classes. Nested classes are another fascinating aspect of Java. They allow you to define a class within another class. This concept enhances code organization, encapsulation, and readability. Visuals, diagram illustrating nested classes. In Java, you can have 4 types of nested classes. 1. Static nested class. A nested class that is static belongs to the outer class rather than to an instance of the outer class. 2. Inner class, non-static nested class. An inner class is non-static and is associated with an instance of the outer class. 3. Local inner class. A class defined within a method, typically for a short-term purpose. 4. Anonymous inner class. A class defined without a name, often used for one-time tasks, such as event handling. Visuals, code snippet illustrating different types of nested classes. Concept 4, benefits of nested classes. Why use nested classes? Here are some benefits. 1. Encapsulation. Nested classes can access private members of the outer class. 2. Logical grouping. They allow you to group related classes together. 3. Improved readability. Nested classes can make your code more readable and organized. Visuals. List of benefits of nested classes. Understanding enumerations and nested classes unlocks new possibilities for creating organized and elegant Java code. Closing shot. The host smiles. Thank you for joining us in this tutorial. If you found this information valuable, please like, subscribe, and hit that notification bell for more Java programming insights. Stay tuned for our next Java adventure. Title: Demystifying Regular Expressions in Java. Your ultimate guide. Opening shot. The host stands in front of a whiteboard with regular expressions in Java written on it, ready to explain the essential concepts of regular expressions. Hello, Java enthusiasts! Today, we're diving deep into the world of regular expressions. Regular expressions, often referred to as regex or regex, are a powerful tool for pattern matching and text manipulation. Let's master the art of regex in Java. Slide 1. Regular expressions in Java. First, let's understand why regular expressions are so important. Concept 1. What are regular expressions? At its core, a regular expression is a sequence of characters that defines a search pattern. It allows you to perform complex searches, replacements, and validations in text data. Visuals. Diagram illustrating a regular expression. In Java, regular expressions are supported through the Java util regex package, which provides classes like pattern and matcher for working with regex. Visuals. Code snippet importing regex-related classes. Concept 2. Basic regex syntax. Let's start with some basic regex syntax. 1. Literals. Characters like letters and numbers match themselves. Visuals. Code snippet illustrating literal matching. 2. Character classes. Square brackets define a character class, allowing you to match any character from the set. Visuals. Code snippet illustrating character class usage. Concept 3. Metacharacters. To perform more advanced operations, you'll need metacharacters. These are special characters with special meanings in regex. 1. Dot. Colon. Matches any character except a new line. Visuals. Code snippet illustrating the dot metacharacter. 2. Asterisk. Matches 0 or more occurrences of the preceding character or group. Visuals. Code snippet illustrating the asterisk metacharacter. 3. Plus. Plus. Matches 1 or more occurrences of the preceding character or group. Visuals. Code snippet illustrating the plus metacharacter. Concept 4. Regex quantifiers. Quantifiers help you specify how many times a character or group should appear. 1. Question mark. Matches 0 or 1 occurrence. Visuals. Code snippet illustrating the question mark quantifier. 2. N. Curly braces define the exact number of occurrences, or a range of occurrences. Visuals. Code snippet illustrating curly braces quantifiers. Concept 5. Common use cases. Regex can be used for a variety of tasks, including 1. Validation. Check if a string matches a specific pattern, e.g., email, phone number. 2. Extraction. Extract data from a text document, e.g., extracting URLs from a web page. 3. Search and replace. Find and replace text based on patterns. Visuals. List of common regex use cases. Regex is a powerful tool, but it can be complex. Take your time to learn and practice it. Closing shot. The host smiles. Thank you for joining us in this tutorial. If you found this information valuable, please like, subscribe, and hit that notification bell for more Java programming insights. Stay tuned for our next Java adventure. Title: Mastering Java Concurrency. Building Robust and Scalable Applications. Opening shot. The host stands in front of a whiteboard with concurrency in Java written on it, ready to explain the complex but crucial concept of concurrency. Hello, Java enthusiasts! Today, we're diving deep into the world of Java concurrency. Concurrency is like a secret sauce that empowers your applications to perform multiple tasks simultaneously, making them robust and scalable. Let's unlock the power of concurrency in Java. Slide 1. Concurrency in Java. First, let's understand why concurrency is so important. Concept 1. What is concurrency? Concurrency is the ability of a program to execute multiple tasks or threads simultaneously. It's like having multiple chefs in a kitchen, each working on different dishes at the same time. Visuals. Diagram illustrating concurrency. In Java, you can achieve concurrency using threads, which are lightweight, independent units of execution. Visuals. Code snippet illustrating thread creation. Concept 2. Thread states and life cycle. Threads in Java go through various states in their life cycle. 1. New, the thread is created but not yet started. 2. Runnable, the thread is running or ready to run. 3. Blocked, the thread is waiting for a resource or condition. 4. Terminated, the thread has finished its execution. Visuals, diagram illustrating thread life cycle. You can control and manage the life cycle of threads in your Java applications. Concept 3. Synchronization. Concurrency can introduce challenges like race conditions and data inconsistency. Synchronization mechanisms in Java help you tackle these issues. 1. Synchronized methods. You can use the synchronized keyword to ensure that only one thread can execute a synchronized method at a time. Visuals, code snippet illustrating synchronized methods. 2. Locks, Java util concurrent locks. Java provides advanced locking mechanisms such as reentrant lock for finer control over thread synchronization. Visuals, code snippet illustrating the use of a reentrant lock. Concept 4. Thread pools. Creating and managing threads manually can be complex. Thread pools provide a convenient way to manage threads efficiently. 1. Thread pool executor. The thread pool executor class in Java allows you to create and manage a pool of worker threads for concurrent tasks. Visuals, code snippet illustrating the use of a thread pool executor. 2. Executors, Java util concurrent. The executors class provides factory methods for creating different types of thread pools, making thread management more accessible. Visuals, code snippet illustrating the use of executors. Concept 5. Java's high-level concurrency utilities. Java offers high-level concurrency utilities in the Java util concurrent package, such as executor service, future, and completion service, to simplify complex concurrency tasks. Visuals, code snippet illustrating the use of executor service. Concept 6. Best practices. To write robust and efficient concurrent code in Java, consider these best practices. 1. Avoid unnecessary synchronization. Minimize synchronization to prevent performance bottlenecks. 2. Use thread-safe data structures. Choose thread-safe collections from Java util concurrent. 3. Proper exception handling. Handle exceptions gracefully in concurrent code to avoid crashes. 4. Testing and profiling. Thoroughly test and profile your concurrent applications for performance optimization. Visuals, list of concurrency best practices. Concurrency is a powerful tool that can unlock the potential of your Java applications. With great power comes great responsibility, so use it wisely. Closing shot. The host smiles. Thank you for joining us in this tutorial. If you found this information valuable, please like, subscribe, and hit that notification bell for more Java programming insights. Stay tuned for our next Java adventure.